So, sorry for the delay. Now I'm up and running. Third lecture on quantitative big imaging, and today I'm going to talk about image enhancements. Now we're going into the topic of image processing, and today I'm going to talk about that unfortunately our images are not perfect, so we got noise and artifacts, and I'm going to talk today about different filters, also going a little bit into the Fourier transform, looking into advanced filters, a little quantitative side using filters, the structure tensor, and then finally, to be able to trust what we have done, also evaluation workflows. And as usual, there is a lot of literature you can look at if you like. In this case, I think the book by Bernd Jehne is pretty good on the topic about filters. And then, of course, you always have John Ross. If you want to look into direction, then you can look at Joseph Bigon's vision with direction. It's an interesting view into how you can use filters to find directions in your images. And finally, also looking into different metrics on how we can quantify how well our filter is actually working. Usual thing, we need a bunch of modules to run this notebook if you want to run it on your own. Doing that, say it again, you should probably clone the repository, and then you can always do a git pull to get the latest updates, and then you can run the Jupyter notebooks from this. I haven't tested it, but I would guess you can also run the notebook through Renku, but that I actually need to test to confirm that it does work that way. It appears that when you click on the links to get the slides on the weekly plan, that the figures don't appear, so there is some kind of linkage problem that I need to fix. So, coming to the topic. When we do a measurement, it's usually not as nice as we would like to have it. So, ideally, you would like to have an image that gives you a cross-section looking like this. Clean, black and white, you have void, you have some material, but that's not the truth. We saw already in the first lecture that we have some blurring. That's from the acquisition system, the optics, also the way you acquire, can be the physics of the whole process that introduces blurring. On top of that, that would be nice if it only was that, but on top of that we have noise of different characters. I'm going to show you some of those in some later slides. And even more, you can have artifacts from the measurement principle, or also again from the interaction between matter and the radiation you're using for your acquisition. So, in the end, the effect of all this is that this very clean, sharp image turns into that you would actually measure. So this is a tomography image where we can see that there are a lot of ring artifacts. I don't see any line artifacts, but that could also be. I think that is one. And this is what we actually see when we do our measurements. Can be better, can be worse, depending on what conditions you could afford or what the instrument can give you. But it's not uncommon to see something like this. So, the different factors that affect the image quality, to put it in bullet points, is first of all the resolution. That's the blurriness that I showed. Then we have noise, and contrast is also actually something that we have to look into. The imaging modality you use may not deliver very much contrast between relevant features and the background and so on, and that is actually also a problem that we have to struggle with. Then inhomogeneous contrast or background, that in different places the contrast is better than in other places, can also be, that's also kind of a measurement artifact. And then, of course, we have the different artifacts that can be outliers of different kinds that produce different kinds of of effects in the image. And when we look at the full image processing chain, we start with the acquisition, which we have already talked about in the first lecture, a little bit in the second lecture. And then comes the next one, is enhancement to produce, say, nice images. And from that on, you do some kind of further analysis. So that could be some segmentation, where you divide the image into different classes. Then you may need to do some post-processing because the segmentation was maybe not as good as possible. And then you do all your quantitative analysis based on the information you have extracted from the previous steps. But today we are essentially looking at the enhancement and how we can do it in different ways, and also how we can verify that it's actually doing the right thing. So, noise and artifacts. Noise, to put it very general abstract, is essentially the information that we don't want in the image. So that is something that is mostly a random contribution, and it typically obscures the information that we are interested in. And there are different types of noise that we can come across. We have the uncorrelated noise. Every pixel has a noise signal which is independent of its neighbors. Then we have event noise. So that would be usually a kind of outlier noise, like salt and pepper. And then we have the structured noise, which actually correlates with its neighbor. And these are the typical types of noise that we can see in an image. Usually all of them are combined, but if we separate them, this is what we can see. And looking at the noise models, the most common one that you see in image processing and signal processing literature is the Gaussian noise. It is a good approximation for most types of noise that you see. It's very easy to model, it's easy to handle, and thanks to the law of the large numbers, everything at some point converges to the Gaussian noise. And you can see here some different examples, how the distribution looks like. So that means that the variation of the values that comes out of this distribution look something like this. So if you have here put some different center values and different width of the Gaussian, and that then also has an effect on how you observe your image. The next one is actually more relevant to most imaging applications, and that's the Poisson noise, which is an event counting noise. And mostly you're counting some kind of event particles. Could be photons, could be neutrons, could be different quantities that you measure. And that one is a bit special because its shape of the distribution changes with the intensity. So it's a kind of a multiplicative noise, and that can be a bit trickier to handle. And if you look as a comparison, I tried here to show the difference that if you have a signal looking like this, a sine wave, and add Gaussian noise, you can see that the band around here is more or less the same. And I also, the big wide bar here, I put in the variance of the signal at that point. If you look at Poisson noise instead, you have a greater variance with higher amplitude than you have down here. And I try to extract, and you can see that this one is essentially a constant band, but this one narrows down for the low intensities. And that is something that we have to look into when we do our filtering, or be aware of when we do our filtering. And actually it's also very important when you do the acquisition, because if you have a very weak input signal, that means you cannot get high amplitude, and then you get the very low noise, this noise in this corner. And If you increase your intensity, then you get that one. And in principle, it looks good. I mean, small variance is good, but it's variance compared to the amplitude, and then it's, as we will see, not so good anymore. Then we have the salt and pepper noise. Typically, it's a type of outlier noise. Exactly the amplitude may vary with the reason why you get it, but in this case, I'm just doing minus and plus 1 as the amplitude. And often it's described with something like a uniform distribution. If it's below some threshold in a uniform distribution, we set a -1. If it's between two limits, then it's a 0, and beyond it, then it's a 1. So our noise fraction for the salt and pepper is then the parts that is in the tails of the distribution. And here we see some examples. We set lambda 1 at 1% and lambda 2 at 99%. That means we have 2% of these outliers in the image. Here we have 10% outliers, and here we have 20% outliers. And yeah, depending on the measurement, you may have these or may not have them. I see them very much in my measurements with the neutrons, because we generate a lot. And as I started mentioning or hinting on with the Poisson noise, we have to measure how strong the noise is compared to the signal, and that we do with the help of the signal-to-noise ratio, which is in principle the mean of the image intensity over the standard deviation of the image intensity. So it's a unitless quantity, and you can't compute this from a whole image, but you have to look into smaller regions that you look where you measure this. And here we have an example with the Poisson noise, and you can see that for a short exposure, this was a 50-second exposure, a 50-millisecond exposure, and this was a 10-second exposure, and you can see that the signal-to-noise ratio is not a straight line. And that is the effect of this shape-shifting of the distribution. And if we look at the reason for it, is that if the standard deviation, the variance is the same as the average value for the Poisson distribution. So if we have n events, that would be the average value. And then the variance would also be n, so the standard deviation is square root of n. So in the end, the signal-to-noise relation is essentially following square root of n. That means if you want to double your signal-to-noise ratio, you have to do 4 times exposure time to achieve that. And that can be pretty expensive after a while. I mean, down here, it doesn't matter so much, but if you say you want double the effect in the signal-to-noise ratio when you already have 10 seconds, then all of a sudden you have to measure 40 seconds. That starts to hurt, in particular if you have limited experiment time. Then I have made a collection of some useful Python functions that you can use for this. One is to generate random signals. That relates a little bit back to last week's lecture, where we had data sets. And one thing of the augmentation is actually to add noise. And this is your toolbox to add noise into your images. Then, of course, you can also do statistics. There we have a lot of NumPy functions. Actually, these are also from NumPy. So we have mean, variance, standard deviation. You can compute mean and max. You can also compute the median and the rank. So these are built-in functions. You don't have to implement them yourself. And it comes quite handy when you start doing comparisons with to see the performance to compute these. So that was that about the noise. Let's switch over to the filtering. So let's do the basic filtering methods. And the first question is, what is a filter at all? So in principle, it is a processing unit that enhances or selects the wanted information, and on the other hand, suppress or completely reject the unwanted information. And that should ideally be done without altering the relevant features beyond recognition, because you can apply a filter that completely destroys everything. You have got rid of noise, but there is no information left. There are different types of filters, and depends on what information you want to amplify or suppress. And the two classic ones, one is the low-pass filter, which preserves slow variations in the image and suppress rapid changes in the image. So here I have the original, where you can see that there is an overlay between two types of signals. One is with high fluctuations and one with slow fluctuations. And if you apply a low-pass filter on that, then you should ideally get only the trend that is in the background. The opposite would be then the high-pass filter, which then extracts the rapid changes in the image, and then the bias is then suppressed. And typically, the first type of filter that you approach is the linear filters, which are computed with the help of the convolution. And then we have the convolution integral, as you probably have seen in your calculus classes many years ago. And this is right now looks like a one-dimensional signal, but it can actually be applied in as many dimensions as you like. The question is to wrap your head around more than 3 dimensions. That's sometimes a bit tricky to get the understanding of it, but in principle you can do it on any number of dimensions. And the important thing here, we have 2 things. One, F is here the image, and H is the convolution kernel, which we apply to the image. And if you want to have a recap on convolution, 1 brown and 3 blues has a very nice illustrative movie where they explain what the convolution is actually doing and demonstrate it visually. Different kernels, so this is in principle what the convolution is doing, is computing a weighted average. So the kernel defines weighted local average. So it defines what are the weights in your filter kernel. It could be the uniform filter or the box filter, which has a uniform distribution of the weights. So it's in principle the local average. Or else you can also take, for example, the shape of the Gaussian as to get the weights from your filtering. That means you have a more weight on the center pixel in the kernel, and then less the further away you get. And if we look at different signal-to-noise ratio, and when we apply the Gauss filter on this little X-ray tux, we have here, in principle, noise-free. So I have SNR 1000. Then we have SNR 10, 5, and 2. And you can see that with a signal-to-noise ratio 2, you can barely see anything. And here it's also essentially unfiltered because the sigma is very small. It's essentially just centering around the center pixel. Then we have sigma 1, and you can see the first thing you can see that there is some blurring. And on this one you can only see the blurring, and then here you can see that actually some of the noise vanishes. And also here it's not so fine-grained noise that you see, and that goes on. And if we even increase the filter kernel to a 3, then we can see that there is actually a trend. If we really want to see it, we could see that there is a tux, but we can't see any details. So the idea when you have high signal to noise, low signal to noise ratio, you can of course apply a large kernel and get rid of the noise, but at the cost of losing image features. So in principle, jumping back to this figure that from lecture 1, we have our image acquisition system with many transfer functions and different types. And finally, we also have some scintillator, which in principle add the scintillator together with the optics as our blur. And adding a filter is actually, in principle, adding yet another modulation transfer function to this acquisition system. And if you have a Gauss filter, that MTF would look something like this. So you can see that in this, we have the sigma, which then determines how much blurring you get through that. So in principle, what you do when you apply a Gauss filter is that you increase the scintillator thickness in your acquisition, or you make a blurrier, have a blurrier optics, but it's easy to see it as a connection to the scintillator. And the effect, we saw already on the Tux example that we get some blurring. So here I have no filtering at all on this test image, where I have a very tiny feature over here, and then increasing size. And on the unfiltered one, you can see that we have nice peaks for everything, and there are no unsharpness, so this is good. If we apply a Gauss filter with a sigma 1, you can already see that this first item has reduced amplitude pretty much. And there is also some spread on the item. And also this one gets a little bit amplitude loss and also some spreading. This one, the next one here, is so wide that you see that it's blurred, but it can still maintain its amplitude because it's so large. And of course, the further one over here, they still are maintaining the amplitude, but a little bit edge unsharpness. Now, if you increase your filter kernel really large, you can see that it's just blurry blobs. And the effect is that they may even merge together. So the smearing is actually starting to overlap, and that you can see over here, that here, these two, or actually all of them, they start overlapping, and you actually have amplitude loss also on all of them now with this filter. So that is a cost that you have to be aware of. Of course, you can improve the signal to noise ratio, but if you lose the image information, you're lost. So a little bit technical dive into how the convolution is computed. A little bit just visualized it. So in principle, what you do, if you have a box filter, you extract a region of pixels, compute the average, so you just extract the numbers here, divide by 9, and then you put that value into the position. So the convolution, if you want to implement it, is a very easy algorithm to implement. You need a couple of loops. The important thing is to put the loops in the right order, otherwise you will wait forever. For those of you who study computer science, this you probably have looked at already, that loop order is important when you perform memory-intense operations. Another interesting thing about the convolution is that for some kernels, you can separate them and into smaller kernels. So we have the important thing is that the associative and commutative laws, they apply to convolution. So these two, they are equivalent. So you can do a convolution AB first and then apply it to C, or you can do A and combine it with the convolution of B and C. And also the ordering doesn't matter. So it's said that the convolution kernel is separable if you can split it into one or to two or more parts, which is very important for the efficiency sometimes. So we have some examples. We have the box filter. All weights are the same. So this 3x3 can actually be split down into a 1x3 and a 3x1. And this, in principle, would reduce our computational overhead. Also, the Gauss filter can be split with these coordinates, so we can have the convolution of the x component and the convolution with the convolution of the y component. When it becomes important is when you want to speed up things. And the advantage is if you have a 3x3 kernel, that would mean that you have 9 multiplications and 8 additions. If you do it separable, separated kernels, then you would have 6 multiplications and 4 additions. And if you have a 3-dimensional kernel, the 27 multiplications goes down to 9 multiplications, and that is in principle a gain. But not so much, actually. If you go to 5, in particular in the 3-dimensional 5 kernel, then you get down from 125 multiplications to 15 multiplications, and then it starts paying off doing it this way. What the theory doesn't say is that there is a call overhead to call the filters, and that sometimes can cost more than the gain of doing this. So you have to actually explore when the filter kernel actually benefits from doing this separation. But usually if you have large kernels, it makes sense. Another filter with low pass characteristics is the medium filter, which has, as I said, a low pass characteristic, but it's not a linear filter. But what you do is you again extract the pixel values in the neighborhood that you have specified, in this case a 3x3 kernel. Then you compute the median, so you sort all these values and take the mid one and place it here. And this is actually a pretty popular filter because it can take out some specific types of noise, and that would be the spots. So if you have salt and pepper noise, the median filter would be the ideal filter for working here. And if you compare, you have this spotty image, you apply the Gauss filter, you can see that each spot is just smeared out, and it still have some speckled appearance in your images. But with the median filter, the image turns pretty much clear. So this looks nice. However, if you apply the filters to an image with Gaussian noise, the Gauss filter is actually stronger against that kind of noise, Gauss noise or Poisson noise or whatever. The median filter also does some kind of smearing effect, and sometimes it's actually not so beneficial to use it. And another thing with the median filter, it in a way destroys the statistical properties of your image. So you can't really use the same, or it's not fully true that you use a Gaussian model after applying a Gaussian noise model when you apply the median filter. So a little example. We have in our measurements, we have spots like those you can see here. Sometimes we have few, sometimes we have very many, and they are pretty annoying. They distort our measurements. If we do tomography, they introduce line artifacts, so we want to get rid of them. In this lecture, I'm going to show some examples, the approaches we could use. We could use a low-pass filter, like the Gauss filter. We can use a median filter, and then I'm going to show an algorithm that actually detects spots and replaces them with some kind of estimate. The algorithm would look something like this, where we have the original image comes in, we apply a median filter, and the median filter removes the spots, but we have some blurring, which we don't want. And then we subtract the median from the original, taking the absolute, and then we get, in principle, an image that only contains spots and no image structure, because we did, in principle, a high-pass filter now. So we only got these spotty details, and then we apply a threshold saying if the amplitude of these speckles are greater than a value, then we say it's an outlier, and then we get our outlier mask, which here I multiply with the median value, and then we get the replacement, but only in the places where there is a spot. The other path would be that the spot or the amplitude of this image is less, and then we get a mask for the pixels that we want to keep. And then we multiply the original with those, and then we sum it, and then we have a cleaned image. So this algorithm has two parameters. One is the width of the median filter, and the other one is the level of threshold for outlier detection. And if we compare these, we have the original with spots and on different places. And if we apply the box filter, you can probably see directly that first, the image is very blurred. And second, as a little bonus, you get really big blobs where the spots were. So you can even see the kernel coming out here in these spots here. The median filter, on the other hand, removes the spots, and you don't see these features at least, but you get some smoothing, and at this point in the processing chain, it's too early to do the smoothing. So this is also not really what we want. And then with this cleaning algorithm, you can see that in principle, it's the same image, but there are no spots. And if we look at the difference, you can see that the box filter does pretty ugly stuff. The median filter takes the outliers, but also cancels some noise. And finally, the cleaning has, in principle, no changes except where there are spots. For those who use image J, there are two ways to get rid of outliers. One is called despeckle, which is in principle just a median filter, so don't use it. If you want to use it, say that you use the median filter, not despeckle. And then there is this remove outliers, which essentially is this algorithm. A little bit differently implemented, but the essence of it is this one. So until now, we have only talked about low-pass filters to get rid of noise. The next type of filter, the high-pass filters, which we a little bit had a glimpse on in the spot cleaning, is to identify rapid changes. And typical high-pass filters that are used are gradients, the Laplacian, and the magnitude of the gradient. And I don't have it's a bit difficult to bring that as kernels. But in principle, the Sobel or magnitude of gradient is 2 times one of these two. And you can also see there are different types of how the gradient is defined, depending on what you want to do. Here you have, say, the classical definition of the gradient. It's just the 2 adjacent pixels, one minus each other, and then divided. So that would be the classical definition. It has a flaw. It's only a 2 pixel kernel, and that means you don't know, or the center point is not handled. So that means you will have a shift of your pixels when you apply this filter. Either you have to say that this is the pixel of importance, or you say that one. But anyway, you will shift your information by 1 pixel. And that can be pretty annoying when you run it afterwards. There are, of course, algorithms that iteratively use this kind of gradient, but then they always do the focus flipping. So in one iteration, they do it that way, and the other iteration, they do it that way. It's also possible. This one is a bit more complicated, But the important thing is that you have a column of zeros here in the middle. That means you have a center pixel, and then it's not shifting anything. And you could, in principle, just take this one, plug a 0 in between, and it would be fine. The advantage of that one is that it's optimized to give you orientations more precise. The orientation estimate will be better. Then we have the Laplacian. There are also very many variations of this one. I think the original definition is -6 in the middle, but depending on how much focus you want to put on the central pixel, you can put a different value in this center point. And if we look at the gradients and look at structure orientations, so if you want to look at vertical edges, you do the dx, and well, the contrast is not ideal, but you can see here that you have the vertical lines. And one more thing you can see is that you have always one dark and one bright line. And that's the falling and rising edges of the structure. Same goes also for the horizontal lines, and also here you can see the alternation between falling and rising edges. And as I'm talking about edges, this is actually one of the main things you use the gradient for, is edge detection. And that's the classic computer vision problem, that you want to detect edges to identify structures. Could be you have a robot going along a corridor, it's a classic one, and you want to see where you have the walls, where you have the doors, where you have the lines for changing from wall to floor, etc. And these are the kind of filters that are used for that. And there are two types. The SOBO, which is the absolute gradient, only produces positive values, or 0 to positive. And that you can also see here, that these segments, they turn out pretty nice. The Laplacian is a bit different because it can give you positive and negative values. And actually, the edge is found at the sign change between positive and negative. That can be beneficial for some algorithms where you really track which direction you're going and then finding this interaction point at the zero crossing. So it depends a little bit on what kind of algorithm you want to develop and what you want to do in the end. But these are the two typical ones that are used for edge detection. And of course, then we have also the relevance for machine learning. Most image processing machine learning models, they build up on convolution. So it's a usually convolutional network where you apply many convolutions and combine them with the help of different weights. And a part of the training is actually defining these convolution kernels, what they look like, and also how much importance they have. In this case, it's the speed limit sign, and it extracts different feature maps. And you can see that some are important, find it more important to see the diagonal structures, other ones horizontal structures and vertical structures. And from that, they can then use it to come closer and closer and identify the most likely speed limit that comes out of this system. In the beginning, when you have large kernels, it looks like the image, but after a while, these kernels look completely crazy. But that is not the topic of this lecture, but the convolution is very intensely used in this field. So this is a good time to take the break. So let's continue afterwards.